My name is Wenqiang. And before my presentation, I want to know how many people here has a smartwatch. Please raise your hand. Okay, not so much, but not so many. But as we all know, the smartwatch sales are growing every year. And we use smartwatch to send message, to make a phone call. We also use smartwatch as a map, as a fitness check, mobile payment, and transportation tickets. So there are a lot of applications with the smartwatch. But as you can see before, there are not many people have a smartwatch. I don't have a smartwatch too. I only have this one to go to the restaurant in our hotel. So what is the problem with the smartwatch? I think firstly, the smartwatch only has a limited screen, so it is so difficult for us to type. Secondly, there is a looming threat to impinge on users' privacy and security. You know that the smartwatch, they have our personal health data, has our message, even the bank account. So it is very important to know how to authenticate the users and enforce access control with such limited screen. And our idea here is we can type on our hand, just like the feature shows here. And with this system, we can also input the password. Interesting is that if the attacker knows your password, but they cannot unlock the screen access to the smartwatch because they have different hand structure and different tapping behaviors. And also, we can unlock and access to the smartwatch with a single tap. Yes, just a single tap, and you can access to the smartwatch. I built a vibration model here, which take into account the mass M, the spring consistent K, and damping coefficient C. I won't go into the details because of the time limitation, but here I want to tell you the inclusions here. The MCK are varied from person to person. So the vibration from different tapping position by different peoples, the vibration has unique profiles. We did a series of feasibility study. Firstly, I put two vibrators on the two persons' hand. And you can see here the vibration response are different from different person. And the vibration are so similar from the same person. And then I asked these two persons to tap their hand. As we can see here now, we have the same conclusion with the first figure in time domain as well as in frequency domain. And then I asked the participants to tap on their hand with 3 different fingers. And the conclusion here is that the distinct signals are generated mainly by hand back associated with the value of MCK rather than a finger itself. I also want to know if I tap on the hand with different force, and the conclusion here is unluckily, the tapping force is an interference factor that needs to be solved. We designed a calibration scheme to check this challenge later. Finally, we tap all the 14 knuckles on the hand, and we can see that all 14 knuckles has unique profiles. So such diversity allows Taprint to distinguish the tapping location, thus creating a small pin pad. The challenge here is, firstly, the IMU may be affected by human mobility and daily actions when we are typing. We may type and walk at the same time, right? And secondly, the tapping signals are passive and unmodulated, so it is difficult to classify these different locations. Third, the hand biometry and tapping behaviors may vary even for the same users over time. Here, I designed 4 kinds of threat model. The first one is the zero effect attack. It means that attackers don't know the password and just try to unlock your smartwatch screen, try to access your smartwatch. And the second one, credential-aware attack. The attackers know your password and try to access to your smartwatch. And then a stronger attacker comes here, and he knows your password number, and he also knows your tapping behavior and try to mimic it. Why I designed the first one, imitate attack. I know that maybe your girlfriend or your wife, your husband, may unlock your iPhone when you are sleeping with your fingerprint, right? So I want to know if the attacker tap on your hand and if it can access to your smartwatch when maybe you are sleeping, right? And this is the architecture of the Taprint system. I will go through the technical details quickly because the time limitation. Firstly, how I can remove the human mobility and the daily actions. Luckily, I find that the human mobility is always less than 10 Hertz. As we all know, we cannot move so fast, like always less than 10 times per second, right? And what about the daily actions? We may type when we hold a fist or taking an object. And we find that all these daily actions are less than, the SNR is less than 5 dB, which is much lower than the tapping vibration. So we can remove this one too. And then I propose a 5-gram vibration extraction to enhance the uniqueness from different positions and maintain the consistency from the same position. And then I use the KNN to classify the different tapping locations. And I also designed a density-based one-class classifier to authenticate the users. Finally, I designed a calibration scheme, including a real-time manual calibration and a multi-thread self-calibration. With this calibration, we can adapt to the different tap force, and also it can allow users to update the training date when error occurs in real time. We implement this system with an LG G Watch smartwatch. We also modify the Linux kernel and improve the sampling rate from 100 Hz to 500 Hz, so we can extract more features. And the experience includes 145 participants. And then I will evaluate this system in 4 parts, from accuracy, security, robustness, and the user study. Firstly is the accuracy. It is quite high, 95%, and the figures below is the evaluation of the technical details. And as I mentioned above before, there are 4 kinds of attack. And under these 4 kinds of attack, the performance is quite well, at least in my opinion. And we also care about the robustness. We test the system in different tap strands with the displacement of the smartwatch or the tap. And also we rotate the arms. We test with different user state, like after the hand wash. Also we test in different environments, like in the subway, in airplane. And we test the system during 1 month. And the performance is still good. Finally, we want to know how the users feel about the distance, and they feel quite positive. And the resultant IP have led to the founding of START, Vaping AI Limited. As I know, this company now already received a seed round investment about 1 million RMB, and they are working on the next round investment about 500 million RMB, which is 5 times than this number. And there is a huge market in this research area. Many companies came to visit our group in Shenzhen University, including Huawei Wearable Research Lab. And interesting, they didn't want to buy the patents, they wanted to buy me. I mean, they wanted to give me an offer. So I know if some students here want to get an offer from this group, and maybe welcome to join in this research area. And here is a demo video. Users can input a password to access the smartwatch. It also works only with a single tap. You can input the numbers, and also it can send a message. Thank you.